welcome back. So we had prepared some slides. A lot of this is repetition. A lot of this is repetition from the morning. Lower?
Get a little lower. But not blocking your face.
Is that good? All right. So we're just going to start off and reiterate a couple important points that we wanted to make about ways that we feel sonomyography is an advantageous way to control prosthesis, and then we'll move on to some more technical discussion about our work towards miniaturizing the ultrasound systems. And
can I just say, is there anyone here who was not here for the morning presentation? Okay, good. Good to know.
Okay. The first point that we'd like to make is that existing myoelectric technology, for the most part, is controlled using surface electromyography. So we're recording muscle activity, electrical activity from the muscles through the skin surface. And this causes some problems in terms of control, which we can understand by considering the sensory motor system as a whole. So if we think about someone with an anatomical arm, they haven't had an amputation, they have motor commands that are sent down from the brain through the spinal cord, out through the nerves, and ultimately arrive at the muscles where they cause a contraction and initiate a movement. Now, when those muscles contract, they trigger what are called proprioceptive receptors that are within the structures in the arm. And these proprioceptive receptors give us a sense of where our body is in the space. And we do have, obviously, other sensory receptors as well. And following an amputation, many of those disappear. But the motor pathways and the proprioceptive pathways are still intact. Now, the problem with a lot of existing myoelectric control technologies is that it becomes difficult for people to access these proprioceptive pathways, because the way in which they're asked to contract their muscles in order to operate the prosthesis doesn't necessarily match with the way that the prosthesis moves. So they're sending commands out to their muscles that doesn't exactly match what the hand is actually doing. And there's this mismatch, then they can make it difficult to figure out how to control the prosthesis. It's not an intuitive control strategy. So this is one of the primary areas that we see our sonomyography system being beneficial. And to reiterate this point, ultrasound, again, is measuring muscle deformation. So as we take that cross-sectional view through the arm, we can see how those muscles' size and shape change over time. And because proprioception, the sense of proprioception, the sense of where your body is in space, is related directly to muscle deformation, there's this direct congruence then between the ultrasound images that we're recording and the sense of proprioception that the subject should be able to access. Yep.
Susannah, that in the previous slide, the color segmentation matching each muscle, is that hand done, or does the system know how to parse the different muscle groups?
Yeah, that's a great question. I should clarify that that image with the colors is just for illustrative purposes. Yep, an actual ultrasound image is not quite so pretty.
Sorry about that.
No, that's a great question.
No, I'm sorry to hear it.
Yeah, it would be great if it looks that perfect. Our jobs would be a lot easier, but it's just for illustrative purposes. Thank you. All right. So I'll skip over this we already talked about earlier. The next point that I want to reiterate is that our training protocol is very quick and very intuitive. As I mentioned this morning, I think there's a sound playing. I don't know if you guys can hear that. Yeah.
That's the video, I think.
Yeah, it's definitely the video.
Okay.
So if you go back once.
It's okay.
It's
Oh.
popped in something. Alright, so essentially what we do is we ask the subject to perform a series of 5 different contractions. So in this video we're asking them to do a key grasp. So they perform this 5 times interspersed with 5 rest phases. And once again, we can extract relevant. Yep.
If you overlaid on that same graph in color, for instance, so you could distinguish it, the waveform moving each of the 5 fingers, would they overlay or would they all be distinctly different?
They will overlay to some extent, but
So potential, so what is that displacement we're seeing on the graph? What are the axes?
so, yeah, the x-axis is time, the y-axis is the correlation between an ultrasound image recorded when the subject's at rest and the current frame.
So different actions don't necessarily discriminate on these graphs.
Right, this will follow the same training procedure for different grasps. It doesn't affect what grasp you're performing in terms of the training, but towards your point, I will say that we are able to very accurately discriminate between those different grasps after training. So what we're looking at here is a confusion matrix. For anyone who's not familiar with looking at these, essentially what we're plotting here is the percentage of the time that someone is intending to perform a specific grasp, and that we actually send that grasp command to the prosthesis. So in an ideal world, we would have a diagonal line of 100% going all the way across. We see not quite 100%, but on average, across 5 different grasps and the 5 different amputees we tested, we had an average accuracy of nearly 97%.
If the response is similar depending on movement, how does the training then distinguish? I don't understand. Excuse me, if I go like this and you get a certain waveform and I go like this, I get the similar waveforms. I do it 5 times. How is it distinguished in the software?
All right, so maybe let's take a step back to the Okay, so we have our training database. It has a series of images that correspond to motion. Yeah.
It's based on the actual image.
Yeah, based on the actual image. So yep.
Keep going.
Yeah, I'll talk through this anyway. So we have this database of reference images. Every time that we record a new image, that image is compared to everything that's in the database, and we calculate correlations between the incoming image and everything in the database. So what comes out is this colorful graph you see here. So these are the actual sonomyographic signals that we're interested in. I know it's a little bit fuzzy to see, but these big peaks that stand out is basically the system identifying that someone is performing a grasp. So there's a very strong correlation between the incoming ultrasound image and something that's in the database. Yeah.
So I want to see if I understand this, because there are 5 grasps.
Yes.
You have a series of photographs of this grasp, and you got a series of photographs for all of the other grasps. At any given moment, you look at the live image and you say, which grasp does this image correlate with? And
Right.
that's what you're looking at.
You know, or more closely resemble.
Okay, that's wonderful.
Right. So
it's pattern analysis, basically, image to image.
Yeah.
But the correlation here is actually, what, pixel to pixel correlation?
Yeah, it's a Pearson's correlation. So yeah, it is basically it's doing pixel wise and then takes a full mean of that. So it's
Okay.
just one number.
Yeah.
Right.
Yeah.
all right. So these correlation signals are then passed to a classifier that uses a.
Oh, there's more. Okay, keep
Well,
going.
that's the last step though. Once we have these correlation signals, then the last step is basically, if we have a peak, so which of the 5 grasps does that course? At that point, it's very straightforward. Send a command to the prosthesis and initiate that grasp.
Cool.
So there is a minor dwell time for the image processing and everything that your video actually shows, like a second delay.
So that delay is not because of processing, that is actually the delay. The hand is actually,
the actuator.
yeah, so it's the
Oh.
controller's delay, not the process. The processing delay is probably less than
It was
20-30%.
it was very. I mean, I've done my electric, and my electric was lagging, and then this it was like there was no lag in here.
So it's milliseconds
Yeah.
of processing time.
But keep in mind that this is happening on MATLAB on a computer, right?
Yeah.
So, yeah,
Okay.
that caveat.
Yeah, okay.
So
An onboard computer would be
the underlying processing thing, I think I now understand. I don't understand how that gives you what you showed before, which is all the intermediate postures.
Right, so that's a great tie into the next point, thank you. All right, so we know that we can very reliably identify rest states and motion completion states. But the question is, what about everything in between? It'd be
Yeah.
great if we could identify those.
Yeah.
It's the same idea here that if we reconsider this training protocol, we do collect ultrasound images that correspond to rest and motion completion, but we can record all the way through that movement as well. So these transition states are detectable. We can follow the same.
So you interpolate.
Mm, yeah, yeah.
Pretty much, yes.
Yeah. So we can identify every step between 0 and 100%. And again, just to drive home this point further, because we are, there's this direct congruence between the user's intended motion, and we can map that all the way across the percentage of movement completion. There's that correlation with the sense of proprioception and the prosthetic hand function. Putting this all together, we do believe that it has enables a much more intuitive control scheme than, yeah.
So you should finish your sentences
Yeah.
when I raise my hand, because my hand's going to go up a lot.
Yeah.
But this is really very interesting. But I haven't understood where muscular proprioception comes in.
Mhm. Yeah, so that goes back to the idea that in order to essentially trigger those proprioceptive receptors, it's directly dependent on muscle deformation. So as the muscle contracts, we gain that sense of proprioception. So if we're able to track that contraction across the entire movement cycle, then we should have access to that proprioceptive cue across the entire movement cycle.
If I may put it in my own words.
Sure.
The way my muscle contraction feels to me is proportional to the muscle contraction, and the sonomyography is detecting the muscle contraction. So you are more closely tracking my feelings than with other techniques.
Yeah, so
Got it.
concise way to put it, yeah.
Thank you.
Yeah. Just to give a more visual example of this positional control, we designed an experiment where people were asked to control the position of a cursor on a screen. So the blue dot that you see on that upper right graph is the cursor. They can move it up and down on the screen, and it moves in direct proportion to the level of muscle contraction. So if it's all the way up at the top of the screen, that's at maximum contraction. And so the task was to try to match the position of that cursor with targets, which is represented by the red line here. And I'll just play a short video. I know it's a little bit hard to see the trace at the bottom, but you can see that he's visually, at least it looks like he's able to kind of match that target position pretty well. And in fact, if you plot this out over a lot of different target positions, what we're looking at here is the blue line corresponds to the position of the cursor that the subject was controlling. And those little diamond shapes, if you can see them, are the target positions. And so you can see there's pretty close, not a lot of discrepancy between the target position and the actual position that the subject was able to achieve. All right, so I showed these videos earlier, but again, putting all these pieces together, we're really optimistic about the opportunities that this control methodology provides for achieving intuitive control and improved functional outcomes. And this is an area of ongoing work in the lab, but for now, we'll move on to the discussion of the miniaturized technology, and I'll turn it over to Fish.
Hello, my name is Biswarup Mukherjee. It's really nice to be here. Thank you for the opportunity. So, all of the work that Susannah highlighted, we...
I don't know when it's done.
Check the connection.
Yeah, the cable and stuff.
There it is. Yeah, so most of the work that Susannah highlighted, so we worked with individuals with upper limb amputation for over a couple of years, and we did this study with clinical ultrasound systems. Now the natural question would be, for most of you who have seen a clinical ultrasound system, it looks kind of like a small mini fridge, right? So how would you get this inside a space maybe this big or even smaller sometimes, right? So to understand why clinical ultrasound systems have not been miniaturized to the extent that we need it to be, we need to understand how it works, right? So let's dive into what goes on inside a clinical ultrasound system. So primarily, an ultrasound system will have two parts, very simplistically, right? So you have an ultrasound transducer. That's the part that you see a clinician holding in his hand and actually navigating on your body to see those images. And then there's the back end, which either looks like a tablet in some cases, sometimes like a mini fridge, which is doing all the hard work, right? So it's doing all the processing. Now, if you break open one of these transducers, what you're going to see is there are individual piezoelectric elements. So piezoelectricity is essentially the phenomena of driving a material with voltage and it generating sound. So in ultrasound, we drive each of these elements with a very high voltage. And what happens is these small elements, they are arranged in an array. Usually you get an array of 64, 128, sometimes even higher counts of these elements. So you get upwards of 64 elements. So it takes up a bit of space, right? So you have an ultrasound array that has 64 elements that's taking up space. So that's one concern. So in order to reduce this form factor, the question is, do we actually need these many sensors? So that's one question. Now, each of these sensors, as I said, gets excited by a voltage, right? So when you're excited by a very high voltage, you send out a small amount of acoustic energy into your body. Now, this acoustic energy is reflected back, and you receive some of that back. Now, the way ultrasound works is that it's looking for echoes, right? So it's almost like a bat hearing out for echoes and trying to locate where an object is. And that recognition of how far the object is comes from the measurement of time. So you measure how long it took for the sound to come back in order to figure out how far that object is. So measurement of time, when it's in the body, it's in the order of centimeters, and at the speed that sound travels in, it's around 1540 meters per second. These time periods are in the order of microseconds. So you're measuring very precise amounts of time, and it's very difficult to measure time that precisely. You need very high speed digitizers, which increases the cost, complexity, power consumption, and the form factor of clinical ultrasound systems. So these challenges make it really difficult to actually miniaturize ultrasound systems. But for our application, the questions are, like I said, is there an optimal number of transducers that we can use and get away by, if you're doing a 5 motion classification, right? All we want to do is a gesture recognition task or a proportional control task. Do we really need 64 sensors? So that's one critical question. Second is, can we image with lower voltage? Can we send out lower voltage pulses? As a result, maybe we'll get a weaker signal, but is that degradation in signal quality acceptable if the task is just to classify images? If you're not bothered about a nice interpretable image, can you get away with these constraints? And finally, can we measure depth without measuring time? So if you don't have to measure time, then you don't need to make very precision measurements with using digitizers. So these are the challenges that we are trying to solve. So in order to understand the first problem, can we pare this down to maybe a few sensors instead of 64 sensors, right? So let's look at what a typical ultrasound image looks like. So you have depth on the y-axis, so you're looking down through the layers of tissue down into your body. And on the y-axis, what you have is the individual scan lines, or the individual elements that have basically passed ultrasound signals into the body, and you stack them together, and you get this nice, beautiful image. Now, as you're scanning through the body in time, you get these stacks of images, and we call these stacks a cine loop. Right? So as you stack most of these images together, as you stack more of these images together, you get a nice cinema loop that shows, you know, your muscles moving. Now, if we select out of those 64 or 128 channels, maybe 3 or 4 channels, right? What we get is what is called an M mode image. M here stands for motion mode. By the way, these images, the depth and scanline images, are called V mode images, or brightness mode images, as opposed to these images on the right, which are called M mode images, motion mode. So what are we seeing here, right? So if I select, let's say, the blue slice, right? So it's a slice that corresponds to one line on a V mode image, and it goes across time. So you're tracking one transducer's image, the image that's coming out of one transducer over time. So along that line, whatever movement you've seen over time, you're going to be able to plot that. So now, this axis is time. So the y-axis in the second row of images is time. So we are looking across the time axis. And the reason why this is called motion mode is because you're now looking at one transducer, and you can really nicely see these movement patterns. If there's an interface that's moving up and down, you can nicely track it. So now we select, so we have a blue scan line, we have a red scan line, and we have a green scan line. So this can correspond to 3 different sensors placed equidistant from each other. And so we get 3 different images, 3 different M mode images. Now if we move if I move my index finger and my middle finger and ring finger, what do we get, right? So if we superimpose these images and we see what sort of patterns emerge out of it, right? So when I move my index finger, what you see is most of the movement is actually mostly restricted to M mode trace 2 and 3. So sensors 2 and 3 pick up that, most of that motion. And even in that, they're actually distinct, right? So if you're just looking at M mode 2 and 3, you can see that, you know, they emerge as distinct patterns. Whereas if you look at the ring finger movement, you see that it's located in all 3 sensors. So you can find information about this movement in all 3 sensors. So even with just 3 sensors, you can see distinct patterns emerge out of 3 different motions that we are looking at here. So that gives us a sense of the fact that if we sparsely sample this nice, beautiful ultrasound image, or if we don't have as many sensors, you can still do really robust classification. So these patterns will emerge out of these sensors. And we have done some formal work where we have systematically shown that if you reduce it down to as low as 4 sensors, you can still retain classification accuracies higher than 90%. And that's really was the key finding that led us to believe that, yes, we can pare it down to just 4 sensors and still get it to work. So from there on, what we did was we developed wearable ultrasound transducer patches. So on the left-hand corner, what you see is if I take one ultrasound transducer, so an ultrasound transducer would be that white dot in between. So each of these elements can be excited electrically, and they would emit sound into the body. So we have 4 such elements. I've only shown 3 here, but there are 4 elements over there. And this is placed on a flexible silicon-based patch. And the electrical signals and the back end of the electronics we will show you later. And this can be placed directly on the skin, and you can tie it with a Velcro strap or something like what Chad was showing, Chad and Marty, you know, with within a socket, and that would be secure on your skin, and it would be able to image through. And the images that you would see from them would look very much like these M-mode images that you see. And we can use this to classify motions. So, yes?
Sorry. So does the piezoelectric transducer is putting out the signal, is it also detecting the echoes?
Yes, yes, yes. Yeah, so that's a great point. So these are not just emitters, these are also receiving the signal and processing it. And so the way we process the signal, that's actually a good segue. So now we have transmitted the signal, we have received it, right? Yes.
Sorry, so to talk about the transducers themselves, when you had, let's say, 300 transducers sort of in an array, right? In a normal sensor, or in a normal scanner, what sort of classification accuracy were you getting? You said when you had 4, you could get 90, but what was the cost?
So the cost was less than 4%.
Wow.
So it's the reason is the data is so rich, and there's a lot of redundancy in the data, right? So muscle bulk, it would be probably, so the largest muscle group in the forearm is probably around 1 square centimeter plus cross section, right? So you don't really need that much information.
Sure.
So by sparse sampling it, you can still get away by doing this. So now we have attached these transducers. What remains to be seen is, the other part of this system where the back end, in order to reduce the bulk of the back end, we really need to move away from traditional ways of processing the signal. We cannot be exciting these transducers with high voltage pulses. High voltage pulse generation requires large circuits. We cannot do that. So we actually adopted a new technology called time delay spectrometry. This was actually developed for radar applications back in the 60s by this genius individual called Richard Heiser. And this was used for a very long time to make acoustic measurements, like how do you soundproof a room? What are the sound characteristics of a room? So time delay spectrometry was used extensively for this application, and we adopted those applications, adopted this technology into ultrasound imaging. And we developed our own system which uses a low voltage pulse and solves many of the problems with the back-end electronics. And so this is one of the boards that basically excites and receives signal from one sensor or one channel. This is still not the ideal form factor that we would like. So this form factor is 5 centimeters by 3.5. The newer generation of this board is going to be around 1.5 centimeters squared. So this is really tiny. So it's going to be the size of a EMG electrode, essentially. So each of these units basically sends out a signal, receives it, processes it, and you have a stack of 4 such sensors, and you can basically control and receive signals from that ultrasound band that I had shown you. So it's receiving from this, and the ultimate image that you get from it would be these M-mode images. Yes?
What sort of voltages do you need in order to get the transducer to operate appropriately?
So I'm simplifying this again, but when you're in a traditional ultrasound system, what you're doing is it's almost like hitting the transducer with a hammer, right? So it's a high voltage, short time pulse. What we are doing is we're spreading that energy out over time. So the total energy is the same, but it's spread out over time. So the voltages that we use are about 2.5 volts peak to peak compared to at least 40 to 100 volts peak to peak. So those are much easier to generate. Yes?
Don't certain remote control toys also use acoustic sensors to detect when they're about to approach a wall?
Correct. And those sensors, they are ultrasound sensors, but they are operating at a much lower frequency. So typically aeroacoustics, so if you're transmitting into the air, you need frequencies of around 100 to 200 kilohertz, sometimes 400 kilohertz, because otherwise it would attenuate a lot. So higher the frequency, higher the attenuation. Inside body, we actually, medical ultrasound imaging, it happens above 1 megahertz.
So I can't take an RC car, press it against my arm,
No
and hope
problem.
it's going to work.
It will work for very shallow depths. So it'll probably be able to see, like maybe half a centimeter inside your body.
Whereas what I need for this application
Would be
is
4 centimeters plus. Yeah, there you go.
4 cars.
4 cars. You need 4 RC cars on your hand. So yeah, so this image, what we're basically trying to show is, as you do different motions, these patterns emerge out of these motions, and we can do this real-time imaging at about 25 Hertz, which is sufficient for most applications, beyond prosthetic control actually. And we get really nice, robust SNR, signal-to-noise ratio of about 30 dB. And we were talking about this in the morning. We have shown that these sensors are safe for long-term use and well below clinical regulatory standards set by the FDA. As far as power consumption is concerned, it's still a little bit high, and we would like to bring it down, but it's still within the range where we can operate it off of a prosthetic battery. Typical 4,000 milliampere hour battery you would probably take about 10% of the battery life, so it would be shortening the battery life by 10%, which is negligible compared to what the hand would actually be consuming. So finally, does this work? So do you get the same kind of classification accuracies? The answer is yes. So we tried classifying with these M-mode images 9 different motions, and we see that, and this is with able-bodied individuals, we see that the classification accuracy is above 94%, almost 95% classification accuracies. Yes?
What happened to motion 1?
What do you mean? Oh, so I actually don't remember what motion 1 is. So usually what we see is there's a large confusion between key grip and power grasp because they look very similar. So it may have been key grip. I'm not too sure what it is, but that's a good question.
So if it was a confusion between 2, we would expect to see that on 2 of them, but we only see it on 1.
Yeah, so that's actually a very good point. Yeah, I'll have to look into it. Thank you.
Okay.
Good point. Yeah. So you've seen this video before, but just to emphasize, so now what you're seeing here is the wearable band on a healthy individual's forearm. This is imaging the cross-section of their forearm with 4 sensors, and that is being classified in real time using a MATLAB-based script, and we can.
How sensitive is positioning of the sensor itself physically on?
Not very much. So we don't actually carefully place this. Well, we have done some analysis that shows that if it's in the upper 40% of your forearm, you do not really need to.
Lateral, just kind of centered?
Just kind of centered. So we are only imaging the extensor muscle group, not the flexor muscle group. I'm sorry, we are only imaging the flexor muscle group, not the extensor muscle group. It would actually help to do both. There are advantages to doing both. But in general, it really doesn't matter. If you do see a degradation in signal quality, maybe it makes sense to move it to a higher muscle bulk. We haven't done tests with individuals with limb loss where positioning might be critical. So, in order to get nice views of the residual musculature, you may have to move it around and play around with it.
I don't know if this is true, but it would seem to me that the closer to the wrist, the shallower the musculature is to the skin, and therefore you might get a stronger signal if you put it.
Correct, yes. I mean, you're right, yeah. So most individuals with limb loss, I mean, at least with transradial amputation, you're not likely to see anything more than, so we want to be as proximal as possible and get away with it.
As proximal.
Yeah, as proximal as possible. So yeah, I think this video is not playing, so I'm not going to try it. So the next step is our long-term research goal would be to miniaturize these to an extent that we can put it inside a prosthetic socket. And we are getting very close to it. So the version 2 of our system is in works. Hopefully we have a grant to get this done in the next year. So, but we see applications of this beyond prosthetics as well. So in general, in motor control research, where you want to see muscle movement intent, this can be a complementary technique to EMG. We are also trying to develop very small sensors and very low-cost sensors that can be paired with, that can be used as a direct control, sonomyographic direct control system to control low-cost prosthetic hands. Yes?
Have you done any sort of investigation into looking at, once a grip is achieved, the intensity of that grip and how the muscles and tendons change under like different intensities?
Right, so that's a, yes, so we have done some studies where, what we do is we present the user with a target, a virtual target, right? And we ask them to achieve it, right? And then we remove this visual feedback, and we ask them to hold on to that object, and we look at the stability of that signal. So how stable are you? How stable is your grip when you're actually not looking at your hand, or you're not looking at that signal? So we see that that signal is pretty stable. You're very good at actually maintaining that level. But if I ask you to leave that object and reacquire that object, you're not very good at it. We are not very good at estimating the position of our fingers or our grasp without actually looking at it. We need either tactile feedback, haptic feedback, or we need visual information to be able to process. And we have shown that there are ways to get around it with even very rudimentary vibrotactile feedback. Yeah, good question.
You mentioned the original system, large, used MATLAB for
Right,
processing.
right.
So the onboard processor, much smaller, obviously, was it proprietary code or?
So the code for now is proprietary, but so this is NSF funded. This is funded through taxpayer dollars, right? So we don't see any reason for holding this back. That being said, I'm not the PI on the ground, so I cannot make promises.
But your internal team wrote your own code
Yes,
for that. You're
yes,
not
yes.
using anything.
No. I mean, we may have used open source and where we have to attribute, but other than that, yeah, it's all proprietary as of now. We are interested in exploring novel haptic technologies to go with this, and we feel there's an acute need for intuitive haptics to go with this intuitive way of controlling devices. So I'll skip these. Thank all my lab members and collaborators, and we are looking for active partners to help individuals with limb loss get to this technology, learn about this technology. We are also looking for subjects and volunteers to participate in the study, so any help in that regard, and technological collaborations are most welcome. Thank you so much for the opportunity. Please feel free to reach out to us if you have ideas and thoughts. Thank you. Thank you very much.